Thank you for coming and welcome to my thesis defense. Today, we're going to talk about low energy interplanetary trajectories using multiple gravity assists. And we're going to start with a motivation. Low energy trajectories are useful in the sense that they can widen the design space of spacecraft missions, spacecraft that need to change their orbital elements. They can do so using the natural dynamics that are given by gravitational assists on bodies. This in turn saves fuel, which extends the lifespan of the spacecraft. And it's also interesting from a dynamical astronomy perspective in that you could have naturally occurring material, such as asteroids or planetary ejecta, that can transfer from one planet to another without any fuel. And all of this behavior is sort of enacted by multi-body dynamics in the form of gravitational assists. In particular, we're questioning whether for a given set of two bodies, we would like to answer if a transfer is even possible, and if so, can a transfer be found? And if so, how long does that transfer take? In answering these questions, we ultimately develop a numerical method that's going to rapidly produce transfer trajectories in discrete time, which could then be used as initial guesses for transfer trajectories in continuous time. To start addressing these questions, we're going to begin with a survey of the toolkit required starting in continuous time. So we're ultimately considering the problem of four bodies. They're all gravitationally interacting, and one of them is basically infinitesimal, so it doesn't really affect the orbits of the other three. And the configuration of the other three bodies are in such a way that two of them orbit the central body in concentric circles. This basically forms the planar concentric circular restricted four-body problem. Immediately, we're going to take the four-body problem and break it into two three-body problems. So we're going to patch it, and we're going to assume that our particle whose motion we're interested in can switch between the systems at some sort of critical orbit, some orbit that connects the two systems. The final and most difficult step, of course, is we're going to find those transfers that happen. We consider one body at a time. So just for diagrammatic purposes, we're going to take the masses M1 and M2, and we're going to put them in the three-body problem, which is a very classical problem. It's non-dimensionalized and parameterized by the mass parameter given by mu. And in particular, it's a Hamiltonian system. So when expressed in an inertial frame, the Hamiltonian takes this form. And what we specifically care about is that this Hamiltonian is time dependent, and what we want is a time independent Hamiltonian. So what we can do is we can actually switch into a rotating frame that aligns the two bodies. It puts them stationary on the x-axis. So this actually induces a time independent Hamiltonian, which makes a constant of motion. So this constant of motion we refer to as the Jacobi constant, and it tells us permissible regions that our particle can go into. So at certain energy levels, we get regions of motion that are broken down into 5 cases. Essentially, what can happen is that the particle P, can be put into any of the white regions shown, right? And it can move around in each white region, but it can never cross the gray. So in this sense, the gray region is called the forbidden realm. It can never enter or touch the forbidden realm. Now, this is the classical type of picture of restricted motion. However, in 1969, McGehee also proved that under certain energy restrictions, there are additional tori in the four-dimensional phase space that, when projected into configuration space, appear as annulus or annuli. And these are a bit different than their forbidden realm. In the case of the forbidden realm, you just can't touch it. But with these projections of tori that form annuli, you can actually enter each one, but you cannot cross the innermost boundary of the inner one, and you cannot cross the outer boundary of the outer one. So that's to say, these are sort of quasi-periodic structures that densely fill an annulus. And if you're going to touch the outer boundary, then you also have to touch this inner boundary. In the case of this research, we're actually going to consider case 5 of the energy interval. With these sort of results, using the exact Hamiltonian out of the way, we're going to start approximating the Hamiltonian in the sense that we're going to let the mass parameter be extremely small. So looking at the figure in the bottom right, what that corresponds to is our mass, or our central mass, M1. It's just going to be very close to the origin. So that's essentially what we're saying. It also means that our secondary mass, M2, is a very small. It's a perturbation of the two-body problem. So we're going to apply a Taylor series expansion to linear order in the mass parameter to the distances that separate the particle from each body, R1 and R2, and we get the following expressions, which, when we plug into the Hamiltonian, gives us a new expression for approximate motion in this sort of system. And this is favorable because it splits it into two terms, one that is independent of the mass parameter, mu, and one that depends linearly on the mass parameter, mu. Under this Hamiltonian, we're essentially describing perturbed Keplerian motion, where far away from the secondary mass, the particle is basically on a two-body ellipse. In this sense, we can kind of write the distance from the origin, which is under the assumption that mu is very small. It's the distance from the central body. And we can also write its energy in terms of the Keplerian orbital elements, our semi-major axis A, our eccentricity E, and true anomaly nu. The question is, what happens when we're near M2, right? That's the interesting part. And what happens looks like the following picture. We're showing a particle P that's basically on a Keplerian orbit when it's far away from M2. So let's just take one of these lines. Let's say the black one, solid black. And what it's corresponding to in time is it's corresponding to this semi-major axis change. So far away from the secondary, it's not changing at all. It's on a solid two-body ellipse. But as it gets closer and closer to the secondary, it is going to have a periapse. This is corresponding to a close approach, which is essentially our gravitational assist. It's affecting an energy kick. And we can see that in the plot on the right, where the solid curve it's fallen just in front of the secondary mass. So it's had a bunch of energy taken out of it, which corresponds to a decrement in its semi-major axis. And completely likewise for the dashed curve, it has a periapse that's just behind the secondary mass. And correspondingly, it received an energy kick, so it increased its semi-major axis. So with the approximated Hamiltonian also comes an approximate constant of motion. We call this the Tisserand parameter, and it takes the following expression, and in particular, it's useful because it takes the Jacobi constant and it expresses it in terms of orbital elements. So we're going to use the same symbol of the Jacobi constant and the Tisserand parameter because for our purposes, we're going to say that they're the same. And like the Jacobi constant, which determined the forbidden realm and permissible regions of motion, the Tisserand parameter determines permissible orbits of P. So this is best illustrated in a diagram with an example of a transfer from Earth to Mars. So what we're saying here is that the particle P is experiencing successive Keplerian orbits that are changing due to close approaches with the secondary, and they change along this energy surface, which is given by a Tisserand parameter. So in this case, the solid blue curve is corresponding to a Tisserand parameter of 3, and likewise for the Mars system, it's along an energy surface. The interesting part is what happens when these energy surfaces collide. You can actually switch between them. So this is in essence what's enabling the process of interplanetary transfer. So in order to analyze these types of behaviors, we're going to switch from continuous time into discrete time by defining a Poincare section for the particle along its apses. So in this case, we write what's called the Keplerian map. And what it's essentially doing is it's updating the orbital elements of the particle along successive periapse passages. So in this case, the orbital elements that we're considering are the argument of periapse in the rotating frame, which is omega, and the energy k. And the actual bit that's affecting the gravitational assist, the energy kicks, are encapsulated in this function that we call f, and it takes the following form. It looks like this. So generically, the kick function is what we call this function f, and it looks like the following curve, where it has the characteristic behavior that it has an extremely sharp gradient towards the middle, like falling right behind the secondary mass. And on either side is corresponding to an energy kick, which is our gravity assist. So just behind M2, which is at omega equals 0, we receive a very large energy kick, right? This is corresponding to that dashed curve in the figure shown in previous slides. And just ahead of it, we lose a bunch of energy through the same method. And this is a completely symmetric type of diagram. The fundamental approach of this research is to consider successive iterates of this map, the Keplerian map. And to illustrate what this might look like, we're going to consider a continuous line of initial conditions that we call gamma 0. So looking at the graph on the right, we're taking initial conditions in our argument of periapse and our energy, and we're plotting the change in semi-major axis. So we just remember that semi-major axis A and our energy are simply inversely related. So it's fine to switch between the two. So gamma 0 is corresponding to this very straight, flat, dashed curve. And we want to consider iterates of it. And we see that there's a gamma 2 there. So how do we get to gamma 2? Well, we put it gamma 0 through the Keplerian map. So to define the next iterate, you just put it through the map. So looking back at the figure, we take gamma 0 and we put it through the Keplerian map, and that gives us gamma 1. So gamma 1 is not shown, but it's actually right here. It looks like the kick function. And then when you take gamma 1 and you put it back through the map, it gives you gamma 2, which is this curve. And we can keep going. So what we're actually showing is we're showing in zoomed in regions of this graph. And so that brings us to the second panel. You can keep going. So 8 iterates later, gamma 2 turns into gamma 10, right? And in this region, it looks like this. And you can just keep going. This type of Keplerian map has rather complicated behavior. And the actual goal is to find the values that were in our initial conditions in gamma 0 that give us the most change in energy for a given amount of iterates. So jumping down to this last panel, we can see that we went up to gamma 25, and the point that changed the most is given by B, and that corresponded to some initial condition in gamma 0. So that's what we're looking for in essence. Now, one feature of the map is that it actually preserves the phase space. So what's being shown here is the comparison of initial conditions of a trajectory that are both iterated in the Keplerian map on the left and integrated using the equations of motion on the right. And we see that for all intents and purposes, these two phase spaces are topologically equivalent. So there are some differences between them. So in the true equations of motion, they have a time reversal symmetry. So we expect that there's a line of symmetry about omega equals 0, which is seen. This symmetry is broken in the Keplerian map. So you can look at this white region, and it's slightly skewed. So it's slightly canted. These white regions, by the way, are resonances. So these will be important. Around each resonance is all of these different kinds of structures emanating from hyperbolic points. So first, inside of each resonance is an elliptic fixed point, which just means you get librational motion. And next to it, this is kind of like a generic behavior. So you have a resonance with an elliptic fixed point, and then alternating, there's a hyperbolic fixed point in between, and then you get another elliptic fixed point. So what's being actually shown here is that at the hyperbolic fixed point, there are these stable manifolds shown in green and these unstable manifolds shown in red that bound regions of phase space, similarly to how the Tisserand parameter is enabling interplanetary transport. These manifold structures bound regions of phase space called lobes. This is actually what is like putting transfer into effect. So all of these lobes can transit phase space, and this is how it's doing it. And at the same time, this is actually answering one of our questions, like, can a transfer be found? The answer is yes, because of the fact that these lobes have finite area, means they have non-zero measure. So if you're randomly scattering initial conditions, you have a non-zero probability that you will eventually pick a trajectory that's going to transfer, which is nice. This shown on the right here is a way to label these resonances. So we'll come back to this in a bit, but the way that we would read this is just for this particular resonance that's filled in, we would say that the particle completes one orbit every time the secondary completes two. So it's just a ratio of how many orbits are being completed by the particle to the planet or the moon. What we ultimately want to do is we want to navigate this phase space. So I'll come back to the text, but first we're going to look at the pictures. So in the Keplerian map, what we're doing is we're starting with an initial condition, and we are iterating it, and we're trying to transfer to a different orbit. So this is corresponding to the like sort of continuous picture that we have ellipses, and they're evolving due to gravitational assists. And we can see that the way that it does this is it has to jump in between these resonances. So for this reason, we call these resonances partial barriers, because you're not allowed to just jump over a resonance. You have to shoot in between them. We can also see this in the different case that we're not considering. So in the bottom left here, we have a controlled particle that's using fuel. And in this case, there was some trajectory found that transfers from an orbit about Earth to an orbit about the Moon, and it took a long time, very long time. But the idea is that you can just use a little bit more fuel, in this case 90 meters per second more fuel, and you can drastically reduce the amount of time that was spent in this transfer because you are like shooting around these resonances. So in this case, we saved 2 years, which is like very significant. In the purposes of this research, we consider uncontrolled particles. So we're not using any type of fuel expenditure. Now, before we can talk about interplanetary transfers, we have to take a digression first into talking about how transfers may be impossible. So this comes in the form of rotational invariant circles. So this is a type of object that exists in the discrete dynamics of the Keplerian map. What they essentially are like, unlike resonances, which are partial barriers, these form complete barriers to the motion. So if you have a rotational invariant circle in your phase space, you cannot pass it under any circumstances. It's an absolute barrier to transport. And this can happen in 2 ways. It can either happen if your mass parameter is just too small, or if the orbit that if your close approach basically isn't close enough. So if you're too far away, then you're going to get a rotational invariant circle. In this regard, it's kind of important to try and find these. And the property of rotational invariant circles that is going to be used is that these circles, which I'm going to start calling Ricks, they form continuous functions on a cylinder, which is our phase space. So they form a graph. That's what we're going to look for. What we're essentially doing is we're going to look for trajectories that don't form graphs, right? We're going to test if our trajectory is continuous and smooth, and we're going to throw out the ones that don't form a graph, and those that should remain should be Ricks. So just to give the idea of what we're all looking at here, we are looking at the phase space of the Keplerian map, and what we're doing is, I guess I should say what we're looking at. So this blue circle is an initial condition, right? And we are looking at orbits, like trajectories of the Keplerian map out to 1,000 iterates as a function of the initial condition. And what we're seeing here is that pretty much everywhere there are not functions. So there's a lot of chaotic motion and quasi-periodic motion, but just the right initial conditions, you get a graph that is our rotational invariant circle. That's what we're looking for. The way that we're going to do this is we're going to consider orbits as a function. So these things don't fill out the phase space in sequential order. They kind of jump around, but we're just going to sort them and treat them as a function. And we're going to impose 2 very quick tests to eliminate like very obviously not functions. These come in the form of an arc length and an amplitude test. So both are very quick, and through trial and error, both tend to be very conservative, like restrictions on finding Ricks. So if you have a Rick, it won't come anywhere close to violating these. Then this eliminates actually a lot of contenders. Then any trajectory that makes it past these, it's going to be checked with its gradient. So we're going to take a numerical derivative, and we're going to check how many times it exceeds the threshold. So what this condition is actually saying is we're trying to give each orbit a fighting chance of being a rotational invariant circle. As we'll see, as we saw, they very quickly like point themselves out that no, I'm not a rotational invariant circle. Like, take me out. So the conditions that we're going to impose is that the gradient can't exceed the threshold of more than 5, more than 50 times, and it can't have more than 4,000 sign changes. So these are just like numerical tests that were implemented by trial and error, and they seem to work pretty well. The most difficult part of trying to find these things is this following case, where we are given a scenario in which we have 2 identical points that have been iterated. And the question is whether a continuous smooth curve fits through all of these points and wraps itself around the cylinder, right? In this case, this would be a rotational invariant circle. That's what we're looking for. But the alternative case is that there's actually another closed loop that also goes through all the points, but it doesn't wrap around the cylinder. It just wraps around on itself on the cylinder. So this is what we would call a librational circle. Similarly to the resonance type of behavior of being a partial barrier, this is also a partial barrier. This is like the fundamental problem. Is it a RIC or is it a librational circle? And in some regard, it sometimes doesn't matter. So these ones on the right, they can correspond to what's called a Can-torus, and they essentially like surround these RICs. So if you find one that is extremely like, it has librational circles that are very narrow, you're basically on it. So, but sometimes it does matter. And the way that you kind of eliminate these librational circles from contention is you just iterate more, and they're going to naturally point themselves out. So what we're looking at here is we have a librational circle that takes well, they don't go in succession, right? They fill out in this sort of weird quasi-periodic way, but it makes a circle. And what we're doing is we're treating it as a function. So you sort all of the points and you just connect the dots, and then you iterate. Well, as you iterate more, this librational circle starts to rotate. And what's special about that is you start to get regions that overlap themselves. So in terms of a gradient test, this is like pick me, like throw me out. It's really picking up tests on the gradient, which is exactly what we want. Now, some trajectories still pass these tests. So there's a final test that's introduced as like a cleanup slop type of thing. And the idea is that if you have a dense curve that actually fills out a function, like a smooth graph, then this angle that's defined between successive points is going to go to 0. So the assumption is that we've heavily iterated the Keplerian map, and so the curve is dense. So this angle should be very small. And similarly to the gradient, we're going to give it like a fighting chance of being a RIC, but if it's not, it's going to naturally point itself out and eliminate itself. So we're just saying, count the number of times that this angle exceeds a certain threshold, in this case 15 degrees. And if it does that more than 50 times, you're out, right? So
these are 3 sequential points.
Yeah, so it's a little bit different than the gradient test. The gradient test is just using these 2 points, the current point and the point in front of it, but this is using the point in front of that. So it's a little bit different. This is all a bit abstract, so it'd be nice to connect it back to the original frames. What we're talking about is we are finding these trajectories in the Keplerian map's phase space that form a graph. And in particular, this one is identified pretty far below where the secondary is, so pretty far away. In the rotating frame, what it corresponds to is it corresponds to a quasi-periodic set of orbits. And what's being shown here is like a discrete amount of orbits, but this is really like a quasi-periodic, very dense annulus. So this is basically the projection of the McGehee tori into configuration space, which is pretty cool. It's saying if you're on this orbit, you can't get any closer than this radius. You have to be at this extent. You have to be on this annulus. When it's transformed into the the inertial frame, you basically fill out an ellipse, but it's not an exact ellipse, it's a surface. It's a quasi-periodic surface. So what's being shown, it has gaps and stuff, but this is really a continuous type of thing. Because of the fact that the RIC is a continuous graph, you have an orbit at every argument of periapse in the rotating frame. What was found is that these RICs tend to appear near resonance regions. So you can kind of label them that way, but what was done was a comprehensive study of how do these RICs change as you change the mass parameter. Basically, where's the RIC located? What we're really concerned with is the first RIC. So you have your secondary, and then you can start moving away from your secondary, right? And then eventually you get too far away. So there's going to be a rotational invariant circle. And we're interested in finding that one, the first one that appears. This was done for the interior map, which corresponds to this lower sign here, 1 minus, and then plus over here. And it was found with a power law, which is actually pretty interesting. This power law defines a chaotic zone, and what is particularly interesting about it is it's far above the sphere of influence that would typically be seen in a 2-body type setting, far above the Hill sphere, which is in a 3-body setting, and it actually agrees pretty well with estimate from Jack Wisdom from I think 1980, which is pretty cool. The fact that they appear near resonances means that we can actually label each of these RICs by a resonance, and that's what we're doing. So we're doing it for the interior. So way slides back, we showed a resonance that was 1, 2. So that was exterior. So again, it shows number of times the particle completes an orbit versus the planet. So here it's switched, like 1, 2, 1 is less than 2. But here we have, for example, 2, 1. So the first thing is bigger. So the particles going faster, so we're in the interior realm. To connect it to the slide previous, we were looking at a RIC that was actually right here. So we were looking at 7-4 resonance, which is a third order resonance. Pretty cool. And finally talk about interplanetary transfers. And we're gonna best describe it by just looking at a picture. So what we're doing now is we're considering both 3-body problems, but together. And in their own systems, they're each located at a semi-major axis of 1 away, but physically they're not at the same location. So we're going to express the units of 1 in terms of the other. So we're going to pick one 3-body problem to be a semi-major axis of 1, and correspondingly the other system is semi-major axis A away from it. And we're also going to let our Tisserand parameter be the same between both systems, just to simplify things. In this case, we're able to switch between these systems at the intersection of the energy surface given by the Tisserand parameter. And it's shown with these orbital elements. Now, I realize I should have drawn this, but what it's corresponding to is this is an ellipse that actually, it comes close to both. What we're actually saying is we want to find the orbit that gets us close enough to one of the bodies that it can perturb us away from the other. So that's essentially what we're doing. One necessary condition to know if this is possible is if you have a switching orbit that lies within or outside of the nearest rotational invariant circle. So in this case, we have 2 bodies. So we're looking at 2 rotational invariant circles. Just look at one at a time. So take like this system, right? This has an interior rotational invariant circle, which is given by this curve. And this system has an exterior rotational invariant circle given by this curve. And the condition is that the switching orbit has to lie in between. Otherwise, it's just not possible. You won't be able to reach that switching orbit. So you won't be able to transfer bodies. So you won't be able to do a transfer, right? That's the idea. Here's like a general diagram of the procedure that's going to be used to actually find a transfer trajectory. What's being shown here is an example of another transfer trajectory from Earth to Mars. And what we've done is we've aligned initial conditions along this switching orbit. And what we're going to do is we're going to iterate these initial conditions in each respective system to the bodies. And if they make it there, it's a transfer. That's the idea. And also, both systems are being shown on the same x-axis, but these systems rotate independently of one another. So when we actually make a comparison of whether an orbit matches with something in the switching orbit, we don't look at the x-axis. We just look, has it matched in the y direction? It could be answered by like a phasing, like what's the right phasing in order to get these things lined up. Numerically, you're never going to actually be able to get an orbit that lands exactly where we want to go. So we're going to consider actually a region where it can end up in. But because of this kind of introduces a bias. Like we've aligned initial conditions on the switching orbit, but then we're putting it into a region of where it should go. So for that reason, we're going to also consider a switching region. So it just needs to make it numerically within some tolerance. So what we're actually going to be doing is we're actually going to be picking initial conditions that don't lie on the switching orbit. They're actually in the middle, and we're going to iterate both directions. We're going to randomly pick initial conditions, and first we're going to iterate towards this switching orbit or switching region, and then of those initial conditions, we will then iterate towards the bodies, right? So we're taking subsets of initial conditions. And then of those initial conditions that made it to the body, those are our transfer trajectories, right? That's the idea. And so this was done, and it was done for a system for a transfer between Earth and Venus, as opposed to Earth and Mars. And it looks like this, which is pretty cool. So what this is showing is we've picked an initial condition towards the middle of our phase space in the Sun-Earth system, and we've iterated it towards the switching region, and it actually ended up right here. And likewise, in the Sun-Venus system, we picked an initial condition shown in blue, and we iterated it towards the switching region, and it ended up here. And these two matched within some acceptable tolerance. And so we took these same initial conditions and we iterated them backwards towards the bodies. And it turned out that they actually fell very close to the actual place that we're wanting to go. So in the Venus system, it basically went to Venus, and in the Earth system, it went to Earth. So in this regard, we call this a transfer trajectory. What's kind of interesting is you can look at this is the phase space of the Keplerian map, and you can see that this is by no means like an optimized trajectory, right? You can see there are regions like right here where it's very dense in points, and you can kind of make out that there are resonances blocking. That's why. And likewise for Venus, it got stuck here and it got stuck here. So this can also be seen in these type of plots. First, what's being shown is the evolution of the orbit's semi-major axis in terms of iterates, and those regions that were dense in their points, they're corresponding to these where they got stuck, like they just couldn't move anymore. And well, they were trying to bypass the resonance that was inhibiting them. So this is the transfer. Now, this one took basically 1,400 years, which for spacecraft applications really doesn't matter. Like, who cares? But it's interesting in the sense of dynamical astronomy, like an asteroid could transfer in that amount of time, which is kind of cool, or planetary ejecta or whatever. Now, one thing to also consider is that you don't have to have an interplanetary system. You could also have a like intermoon system. So in these types of problems, the time scale is much, much smaller. So instead of 1,400 years, it could instead be 1,400 days. And suddenly that's very attainable. Like, that's possible. In closing, in brief summary, like, what was the purpose of this research? The purpose of this research was to more or less like highlight regions of this phase space very, very rapidly, to try and get an idea of like, where should I pick an initial condition in order to make a transfer in a continuous system? That's the main idea. This approach works for both interplanetary and moon systems, and one necessary condition to make it work is that you have to have there can't be any blockage, no rotational invariant circles. These gravitational assist effects take place way beyond the sphere of influence in the Hill sphere, and in terms of this small example, the expected interplanetary transit time is at least 1,000 years. Thanks.
If you appreciated this video, please like and subscribe. There are links and other materials in the description.